Hi, well, I'm here to help you out with some details on the Carnot cycle. And remember that the Carnot cycle, it's a cyclic process that we take an ideal gas through. All the steps are reversible, so I've labeled this vertical axis P or P external because the gas is always in mechanical equilibrium or pretty close to it. And there are 4 steps in the Carnot cycle. Step 1 is this isothermal expansion while the gas is connected to this hot reservoir, which I labeled TH here, so it's an isothermal reversible expansion. And that takes us from our initial volume, VA, out to VB. Now, step 2, that's an adiabatic reversible expansion, and since it's adiabatic and reversible, the temperature of the gas will cool down, and I've labeled it to cool down to this second temperature, TC. TC is going to be the cold reservoir, and that takes us out to an even higher volume, VC. The third step is another isothermal reversible process, but now it's a compression. And here's a kind of an important point. It's clear that we mustn't go too far in doing this isothermal compression at the cold temperature, because if you overshoot, then when we do this final adiabatic leg, it won't take us back to the initial state of the gas. And so we'll just go to a particular point here, VD, and then the last step, step 4, is this adiabatic reversible compression back to our initial volume. Now, the reason I mention that relationship between these volumes is that, as it turns out, the ratio of VB to VA equals the ratio of VC to VD, okay, which I've written right here. And that ratio I'm just going to define as being R. Okay, so one of the things that we're going to want out of this is the efficiency of this heat engine. W is the negative of the work. Now, it's called a heat engine because we expect work to come out of this. Therefore, we expect that W will be negative, and the minus W will make this a positive number, divided by QH. QH is, if this were a thermal power plant, QH would have been the amount of heat that we had to put in, say, in the coal into the furnace in order to make that first expansion happen and turn the turbine and all that. So there's that. Now what I want to move to is our analysis here. So the first step, step 1, that's our isothermal expansion connected to the hot reservoir, and we know what that is. That's nRT hot, I'll call it, because that's connected to that there, times natural log of, well, it's going to be the log of VB divided by VA, and I've already defined that to be R, so I'm just going to call that natural log of R. All right, and now what about the next step? Well, the next step is easy. That's an adiabatic expansion, so I know Q is 0. How about the third step? That's going to be a compression from volume VC back to VD. So that's going to be NR. Now I need to put a T cold here because it's connected to the cold reservoir. And natural log of what? Well, it's going to be the natural log of VD over VC, which is the inverse of this. So I'll say natural log of 1 over R. Okay, and now the fourth step, that's just another adiabatic process, and so that's that. Okay, I think we can pretty easily figure out what the total heat was. Remember, heat's going to go into the gas during that part. It's going to get squeezed out of the gas during that second, step 3. So that's the heat that goes in. That's the heat that's going to come out. I see I have an NR in common. This log of 1R I could convert into a minus log of R, in which case we have a common factor of NR and log R. What's left over then is the T hot and the T cold. When we inverted this, it made a minus, and so I'm going to say the net must be equal to NR times T hot minus T cold divided by natural log of R. Okay, so that's the total amount of heat that goes in, and so there we have that formula. And now what we want to do is we want to say well, I guess I can finish another little bit of this. I know that since Q is equal to that formula, and we return the gas to its initial state, obviously W, the net W is just minus Q, and of course delta U for the entire process is 0. But what I want to get to is this idea of the efficiency. How much work did we get out divided by how much heat we had to put into this process? Well, let's see the work we've just done here. It's minus all that, and so I'll say that's equal to, oh, well, there's a minus sign in front already, so those cancel out. So I just get NR, and now I'm going to call that delta T, okay, times the natural log of that ratio. Okay, and now divided by Q hot, well, this was Q hot right here, so that looks like NR T hot, natural log of R, because that's what that is. Okay, and obviously that goes away, log R goes away, and we end up that the efficiency of this heat engine is delta T divided by T hot, and that's our result for the efficiency of this reversible heat engine.